Right now, at this exact moment, the James Webb Space Telescope is staring at something that should not exist. Not in the way that science sometimes uses that phrase as shorthand for surprising or unexpected. In a literal sense, the object it measured, the light it captured, the data it sent back to a team of researchers who had spent years preparing for exactly this kind of observation produced numbers that existing physics does not have a mechanism to produce. One of the authors of the paper describing the finding used a specific word to characterize what they were, looking at not anomalous, not puzzling, not inconsistent with current models, impossible. That word appears in a peer-reviewed scientific publication written by credentialed researchers and passed through the review process of one of the most rigorous journals in astrophysics. And it is sitting there in the text, not as hyperbole, not as frustration, but as the most precise word the authors could find to describe what the data actually showed. Stay with me, because this story does not start with James Webb. It starts with a problem that has been building quietly inside cosmology for nearly 3 decades. A problem that the most powerful telescope ever built was not designed to solve, but may have just made dramatically worse. And the reason it matters, the reason it reaches back from the edge of the observable universe all the way to the ground beneath your feet, is something the headlines have almost entirely missed. Subscribe now if this is the kind of story you come here for, because what Webb is finding at the edge of everything is going to keep getting stranger, and you are going to want context before the next paper drops. Let's go back to the beginning. In 1929, an astronomer named Edwin Hubble made a measurement that changed everything. Working at the Mount Wilson Observatory in California using a telescope that at the time represented the cutting edge of what human engineering could produce, he confirmed, something that several theorists had predicted but nobody had yet proven from direct observation. The universe is expanding. Every galaxy is moving away from every other galaxy. The further away a galaxy is, the faster it is receding. Space itself is stretching, carrying everything embedded in it outward in every direction simultaneously. This discovery did several things at once. It confirmed that the universe had a beginning. It established that if you run the expansion backward far enough, everything we can observe converges to a single point at a single moment. It gave cosmology its central organizing framework, and it created a question that physicists have been wrestling with ever since. If the universe is expanding, what is driving that expansion? What is the engine? For most of the 20th century, the working assumption was gravity. The universe began expanding from a hot, dense initial state. Gravity, the mutual attraction between all matter, was gradually slowing that expansion down. Eventually, depending on how much matter the universe contained, that expansion would either slow to a stop and reverse into a collapse, or slow indefinitely and continue forever at a decreasing rate. The universe was in this picture, running down, coasting on the momentum of its own beginning, gradually breaking. That picture did not survive contact with the data. In 1998, 2 independent teams of astronomers, both studying a specific type of exploding star called a Type Ia supernova, made a measurement that nobody expected and nobody wanted. They were using these supernovae as distance markers, just standard candles whose intrinsic brightness is known well enough to calculate how far away they are by how dim they appear. The plan was to measure the expansion rate of the universe across cosmic time and confirm the expected deceleration. Instead, both teams found the same thing. The expansion of the universe is not slowing down, it is speeding up. The universe is not coasting. Something is actively pushing it apart, accelerating the separation between every galaxy and every other galaxy, growing stronger over time rather than weaker. They called it dark energy. Not because anyone knew what it was, because they needed a name for something they could measure but could not explain, could not directly detect, could not fit into any existing framework without inserting it as an external term, a placeholder for ignorance dressed in mathematical clothing. Dark energy now accounts for approximately 68% of the total energy content of the universe in the standard cosmological model. It is the dominant component of everything, and nobody knows what it is. Not in the way that scientists sometimes say they do not know something while actually having a strong working hypothesis. In the deeper sense, the leading theoretical explanation for dark energy, a property of empty space, called the cosmological constant, predicts a value for that energy that is off from the measured value by a factor of 10 to the power of 120. That is not a rounding error. That is the largest discrepancy between a theoretical prediction and an experimental measurement in the history of physics. Some physicists have called it the worst prediction ever made by a physical theory that is otherwise extraordinarily successful. That is the problem that was already sitting inside cosmology before James Webb launched, already unresolved, already threatening the foundations of the standard model, and now Webb has added something to it. Here's what the James Webb Space Telescope actually is, because most descriptions of it focus on the engineering superlatives and miss the specific capability that made the finding possible. Webb launched on December 25, 2021, after decades of development, cost overruns, delays, and a final price tag approaching $10 billion. It operates at a distance of approximately 1.5 million kilometers from Earth, stationed at a gravitationally stable point called L2, where the gravitational pulls of the Earth and the Sun balance in a way that allows it to maintain a fixed orientation relative to both. Its primary mirror is 6.5 meters across, made from 18 hexagonal segments of beryllium coated in gold, chosen because gold reflects infrared light with exceptional efficiency. It is shielded from the heat of the Sun, Earth, and Moon by a 5-layer sun shield the size of a tennis court, keeping its instruments cool to within a few degrees of absolute zero so that their own thermal emissions do not contaminate the faint infrared signals they are designed to detect. All of this engineering serves one core purpose. Webb sees in infrared, and that matters for a specific physical reason. As the universe expands, the light traveling through it gets stretched. A photon that left a distant galaxy as ultraviolet, or visible light, billions of years ago, arrives at our detectors shifted toward longer wavelengths, toward red, toward infrared, toward wavelengths that no optical telescope can detect, but that Webb was built to read with extraordinary precision. The further away the source, the older the light, the more it has been stretched, the more infrared it becomes. Webb can see things that are so far away, so old, so deeply redshifted that no previous telescope could have detected them at all. In practical terms, Webb can see galaxies that formed within the first few hundred million years after the Big Bang. It can look back across more than 13 billion years of cosmic time. It can observe the universe as it was when it was less than 5% of its current age. And what it has been finding in that early universe consistently across multiple observation programs, multiple independent research teams, multiple published papers, is something that the standard cosmological model does not predict and cannot easily accommodate: galaxies that are too big, too bright, too structured, too massive, too mature. Let's be precise about what that means, because this is where the story stops being about abstract cosmology and starts being about something that challenges the entire framework physicists use to describe how the universe works. The standard model of cosmology, the Lambda Cold Dark Matter model, makes specific predictions about how structure forms in the early universe. It begins with the initial conditions established by the Big Bang, applies the known physics of gravity, dark matter, dark energy, and ordinary matter, and generates a timeline. Gas clouds collapse under gravity, dark matter halos form first, ordinary matter falls into those halos, stars ignite. Galaxies assemble gradually, starting small, merging over time, building up mass and structure across billions of years. This process takes time, significant time. The model predicts that in the very early universe, within the first billion years after the Big Bang, galaxies should be small, irregular, chaotic, still in the early stages of assembly. Massive, well-structured galaxies, the kind with organized spiral arms, stable stellar populations, high stellar masses, should not yet exist. The physics of structure formation simply does not have enough time to build them. Webb has found them repeatedly, beginning with early results published in 2022 and continuing through a series of increasingly detailed observations. Webb has detected galaxies in the very early universe that are significantly more massive, more luminous, and more, the structuralies, mature than the standard model predicts should be possible, not one or two outliers that could be explained as statistical flukes. A population, a consistent pattern across multiple independent surveys, multiple research teams, multiple observational programs pointing at different regions of the sky. One landmark study published in the journal Nature in 2023 by a team led by researchers at the University of Edinburgh identified a sample of massive galaxies existing approximately 500 to 700 million years after the Big Bang, each containing stellar masses comparable to the Milky Way, a galaxy that took roughly 13 billion years to accumulate its current mass. These galaxies had accomplished in less than 700 million years what our own galaxy took more than 13 billion years to do. The lead author described the finding as, in their words, similar to discovering a fully built skyscraper in a neighborhood where the concrete was only poured last week. That is the context. That is what was already established before the finding that introduced the word impossible into the conversation. Now, here is what Webb measured. And here is where the story changes register entirely. In late 2024, a team of researchers using Webb's NIR-SPEC instrument, a near-infrared spectrograph capable of reading the precise chemical and physical signatures encoded in the light arriving from distant sources, completed an observation. A program targeting a specific set of objects at extreme redshift. objects so distant that the light they are receiving left its source more than 13.4 billion years ago. Light that has been traveling through an expanding universe for longer than the Earth has existed by a factor of 3, light from a time when the universe was approximately 300 million years old. What they found in that light, encoded in the specific wavelengths of the spectrum returning from these objects, was not just mass, not just luminosity, not just the familiar signature of stars and gas assembled earlier than the model predicts. It was something more specific and more difficult to explain. Organized rotation, these objects are not just massive, they're spinning coherently in a way that requires not only the formation of enormous stellar mass, but the organization of that mass into a stable, rotating disk structure. A configuration that in the standard model requires a sequence of events, gas accretion, angular momentum transfer, gravitational settling, feedback from star formation that takes time. Substantial time. Time that the universe, at 300 million years old, simply had not yet had. The paper describing this finding, submitted to a major astrophysics journal and posted to the preprint server ARXIV, where it immediately drew attention from researchers across the field, contained a section in which the authors attempted to reconcile what they had measured with what the standard model predicts should have been possible. That reconciliation failed. The authors stated directly that within the framework of Lambda CDM, the formation of rotationally supported disk structures at this redshift is not consistent with current theoretical predictions. They use the word impossible, not as drama, as precision. Stop and sit with that for a moment, because the implications of that word in that context and that publication are not small. The Lambda Cold Dark Matter model is not a guess. It is not a rough sketch. It is the product of decades of observational data, theoretical refinement, and predictive success across an enormous range of scales and phenomena. It successfully describes the large-scale structure of the universe, the distribution of galaxies, the pattern of temperature fluctuations in the cosmic microwave background, and the abundance of light elements produced in the first minutes after the Big Bang. It is the most tested and most successful cosmological framework ever constructed. And a peer-reviewed paper is now describing an observation it cannot accommodate as impossible within that framework. There are 3 ways to respond to a finding like this, and the scientific community is currently working through all 3 simultaneously. The first is instrumental error. Webb is a new telescope. Its calibration is still being refined. Its instruments are operating in a regime extreme redshift, extreme faintness, extreme distance, where the potential for systematic error is real. It is possible that some portion of what is being interpreted as organized rotation is an artifact of how the light is being processed, how the spectra are being analyzed, how the redshifts are being determined. This is a serious possibility that researchers are actively investigating. Multiple independent groups are re-examining the data using different analysis pipelines and different calibration assumptions, different methodological approaches, and the scientific process is working as it should. So the second is astrophysical mechanism. Perhaps the standard model is correct in its broad architecture, but incomplete in some specific detail that could, if corrected, accommodate these observations without requiring the whole framework to be rebuilt. Perhaps star formation in the early universe was dramatically more efficient than current models assume. Perhaps certain feedback processes that regulate star formation in later epochs were suppressed in the earliest galaxies, allowing mass to accumulate faster. Perhaps the initial conditions after the Big Bang allowed for faster gravitational collapse in certain regions. These modifications would not destroy the standard model, they would extend and refine it. Several groups are currently developing and testing exactly these kinds of modifications. The third possibility is the one that nobody wants to confront directly, but that the data is beginning to make unavoidable. Perhaps something about the foundational assumptions of Lambda CDM is wrong. Perhaps the nature of dark matter, which provides the gravitational scaffolding on which galaxies form in the standard model, is different from what has been assumed. Perhaps dark energy does not behave as a simple cosmological constant, but has a more complex character that affected structure formation in the early universe differently than the model predicts. Perhaps the initial conditions of the universe, the spectrum of density fluctuations that seeded all subsequent structure, are different from the ones inferred from the cosmic microwave background. Perhaps something more fundamental is at stake. This is not a comfortable place for cosmology to be, and Webb has put it there. Here is the part of the story that the coverage almost always misses, the reason it reaches back from the edge of the observable universe to something that matters here. The standard cosmological model is not just an abstract description of distant galaxies, it is the framework through which physicists understand the history and future of everything. The age of the universe, the amount of matter it contains, the nature of the dark components that dominate its energy budget, the timeline of its expansion, the eventual fate of every structure within it. All of these are outputs of the model. All of them are connected. If the model is wrong about structure formation in the early universe, the wrongness does not stay confined to that corner of the problem. It propagates. Dark matter, the invisible component whose gravitational influence provides the scaffolding for galaxy formation in the standard model, has never been directly detected. Every piece of evidence for its existence is indirect, inferred from gravitational effects from galaxy rotation curves, from gravitational lensing, from the pattern of large-scale structure. If the standard model's predictions about how dark matter drives structure formation are wrong in the early universe, that wrongness touches the entire dark matter picture. It raises the question of whether dark matter behaves differently than assumed, or whether the phenomenon being attributed to dark matter has a different explanation entirely. Dark energy carries the same weight. If the model's predictions about the rate of structure formation are wrong, and dark energy is one of the parameters controlling that rate, then the characterization of dark energy embedded in the model comes under pressure too. The cosmological constant, that placeholder for ignorance, accounting for 68% of the universe's energy content, is already under stress from the Hubble tension, a separate and persistent disagreement between different measurements of the universe's current expansion rate. Webb's early galaxy findings add a different kind of stress from a different direction. These are not separate problems, they are symptoms pointing at the same body, and that body is the standard model of cosmology, which is currently facing more simultaneous pressure from more independent directions than at any point in its history. Now let's talk about what happens next, because the story is not waiting. Webb is still observing. Every cycle of its observation program adds more data to the picture. The early galaxy findings that produce the word impossible are not a single isolated result. They are the leading edge of an ongoing observational campaign that is systematically mapping the early universe with a resolution and sensitivity that no previous instrument could achieve. Every new confirmed massive early galaxy, every new detection of organized structure at extreme redshift, every new spectroscopic measurement of rotation or chemical composition in objects that should not yet have had time to develop these properties adds another data point to a pattern that is becoming harder to dismiss. Several major follow-up programs are already underway. The Cosmic Evolution Early Release Science Survey, one of Webb's flagship observational programs, is specifically designed to characterize galaxies across a wide range of redshifts and cosmic epochs, providing the statistical sample needed to determine whether what has been found so far is representative or exceptional. Early results from this program have consistently confirmed and in some cases exceeded the surprising findings. From the initial Webb observations, simultaneously theorists are working overtime. The finding of organized rotation at extreme redshift has triggered a wave of theoretical papers attempting to identify mechanisms that could produce such structures within or near the boundaries of the standard model. Some of these papers propose modifications to the properties of dark matter that would allow faster halo formation and earlier disk assembly. Others propose changes to the star formation efficiency prescriptions built into cosmological simulations. Others take more radical positions, questioning foundational assumptions about the nature of gravity on cosmological scales or the character of the initial conditions that seeded all subsequent structure. None of these theoretical responses has yet produced a solution that fits all the data simultaneously without introducing new problems elsewhere. This is normal in science. It is the expected shape of a field genuinely wrestling with unexpected observations. But the fact that the wrestling is happening and the fact that the responses are coming from multiple directions rather than converging on a single modification to the standard picture suggests that what Webb has found is not a simple gap that a simple fix will close. There is a deeper issue sitting underneath all of this that deserves to be stated plainly. Webb was built to test the standard model, not to break it. Its primary science goals were defined within a cosmological framework that everybody involved in its design and operation assumed was broadly correct. The observation programs were designed to fill in details, to push the boundaries of what could be observed, to confirm and refine the picture that decades of prior observations had established. The expectation was refinement, not revolution. What Webb is delivering in program after program, paper after paper, is data that fits poorly into the picture it was built to refine. Not dramatically, catastrophically, obviously wrong, in a way that announces itself as a crisis. Quietly, persistently, consistently wrong in a way that accumulates. Galaxy after galaxy arriving too early, too massive, too organized, and too mature. Each individual case explainable perhaps by some specific astrophysical mechanism. that the model does not currently include, but the pattern, the consistent direction of the discrepancy, the fact that the observations always push in the same direction away from the model's predictions, rather than scattering randomly around. Them is the kind of signal that historically in physics has preceded the recognition that something foundational needs to change. The history of cosmology is the history of observations forcing frameworks to expand. Hubble's measurement of the expanding universe forced the abandonment of a static cosmos that Einstein himself had assumed. As a starting point, the 1998 supernova measurements forced the insertion of dark energy into a model that had no place for it. Every time the data in the framework came into sustained conflict, the framework eventually changed. Not always immediately, not always without resistance, but eventually, because that is how science works, the data wins. Webb's data is not done arriving. Here is what you need to hold in your mind when you hear the next paper reported, when the next Webb result appears in the headlines, when the next description of an impossibly early, impossibly massive, impossibly structured galaxy appears in the science news. The word impossible in that paper does not mean wrong. It does not mean fabricated. It does not mean that the telescope malfunctioned or the researchers made an error. It means that what was measured does not fit what the most successful cosmological framework ever built predicts should be possible. That is a different kind of impossible, not the impossible of magic tricks. The impossible of a measurement that tells you your map of the territory is incomplete. Maps get redrawn, frameworks get extended or replaced. The history of physics is the history of models that worked until they didn't, followed by new models that worked better until they encountered something that didn't fit those either, followed by the slow, difficult, contested, thrilling process of building something more complete. We are somewhere in the middle of that process right now. The data is already in, the implications are still being absorbed, the theorists are still reaching for the framework that will contain it cleanly, and Webb is still staring at the edge of everything, still taking spectra, still reading the light that left its sources before our planet existed, still returning data that the model built to describe it did not predict. One paper has already used the word impossible. It will not be the last. What this means in the immediate term is specific and worth understanding clearly. The standard model of cosmology is not about to collapse next week. Frameworks of this scope and this degree of empirical support do not collapse. They accumulate pressure over time until the pressure becomes sufficient to drive a fundamental revision. That revision, when it comes, will not erase everything the standard model correctly predicted. It will extend the framework to accommodate what the standard model cannot currently explain. This is how physics progresses. It always has been. But the finding that prompted the word impossible is not a minor data point at the margins. It is a direct challenge to the timeline of structure formation, which is one of the central predictions of the model. Organized rotating disk galaxies at 300 million years post-Big Bang are not a detail. They are a structural feature of the early universe that the model says should not yet exist. And they exist, measured, confirmed, published, sitting in the dataset that Webb is building, observation by observation from a gravitationally stable point 1.5 million kilometers from Earth, slowly assembling a picture of the early universe that nobody fully anticipated. The researchers who built the standard model, who spent careers testing it, who staked reputations on its predictions, are looking at this data. They are not dismissing it. Some of them are the ones publishing the papers describing the problem. Science is not defended by its practitioners against the data. It is driven forward by the data, however inconvenient the direction. This is the most extraordinary time in the history of cosmology since 1998, and almost none of the coverage of Webb's results has communicated what is actually at stake. There is one more thing worth saying before this is over, about what it means to build a telescope that finds something its builders did not expect. The engineers and scientists who designed Webb spent 25 years getting it to L2. They fought through budget crises, technical failures, a launch delay that stretched years beyond the original Schedule A. Mirror deployment sequence so complex and so irreversible that the project scientists described the launch period as 344 single points of failure. Every one of those points had to succeed. Every mirror segment had to unfold correctly in the cold of deep space, guided by commands sent from the ground with no ability to intervene physically if anything went wrong. They built it to answer questions. They are getting answers. The answers are not the ones the questions assumed. And that in the deepest sense is exactly what science is supposed to do. Not confirm what we already believe, not fill in the details of a picture we already know, push into the territory where the map runs out, and return with information about what is actually there, regardless of whether what is actually there matches what we expected. Webb is returning that information now. It has been returning it since its first science images in 2022, And what it is building, paper by paper, observation by observation, impossible by impossible, is a new picture of the early universe, one that does not yet have a complete theoretical framework to contain it, one that is forcing cosmology to ask questions it thought it had already answered. The edge of the observable universe is not empty. It is not quiet. It is not the smooth, simple, gradually assembling place the model predicted. It is full of structure that arrived too early, mass that accumulated too fast, organization that emerged before the physics of organization should have had time to operate. And somewhere out there, at a redshift so extreme that the light-reaching Webb left its source before our solar system's atoms had condensed into their current form, the galaxy is rotating. Coherently. Measurably. Impossibly. Webb is still looking, the data is still coming, and the word the paper used is the most precise word available for what the numbers actually show. If this is the kind of story you come here for, subscribe now and turn on notifications, because the next round of Webb results is already scheduled. The theoretical responses are already being written, and the conversation about what this means for cosmology, for dark matter, for dark energy, for the Standard Model is only just beginning. This channel covers what the data actually shows at the weight it actually deserves without softening what the papers say. The next result is coming. You will want to have already understood what you are watching. The signal from the edge of everything is still arriving,